from Belgium. The organizing committee asked me to chair this session, so I was really happy with that. And then I would like to introduce Professor Lu. He received his PhD in orthopedic engineering from the University of Oxford in 1997 and worked as, during 1 year as a junior research fellow at the St. Peter's College, Oxford University, and another year as an assistant professor at the School of Physical Education at the China Medical University. He joined the National Taiwan University in 1999, where he is now a professor of biomechanical engineering at the Institute of Biomedical Engineering and a joint professor at orthopedics, the Department of Orthopedic Surgery and the School of Occupational Therapy. He was the director of the NTU Rehabilitation Engineering Research Institute and is currently head of Assistive Technological Division of the NTU Health Science and Wellness Center. He's also the president of the 3D Analysis of Human Movement group of the ISB, and he has published a lot. He has over 145 peer-reviewed journal papers and over 300 conference papers. He's also the editor-in-chief of the Biomedical Engineering, and he's gonna give us a lecture about image-based measurement and biomechanical analysis of the knee joint during functional activities. Thank you, Professor Lu.
Thank you very much. Good morning, everyone, and thank you very much for the introduction from Madame Chairperson. I'm sorry that I cannot pronounce the name properly, so I apologize for that. And first of all, I would like to thank the organizing committee for inviting me here. It is really a great honor to be here to share with you some of our works on medical image-based measurement technology and analysis methods. And I'm going to talk about the applications of the techniques on the knee joint during functional activities. As I'm sure you all know, that the knee joint is one of the most commonly injured sports injuries, making up about 55% of all sports injuries. And we know that mobility and stability of the knee are controlled by a complex interaction between the force-bearing structures, including articular surfaces, ligaments, and muscles. On the other hand, the motion of the knee, as you can see from the animation here, also determines the lines of action of the lever arms of the force-bearing structures, which has important consequences and effects on the performance of the knee. On the animation here, the knee is controlled by the two cruciate ligaments, and the lines of action of the patellar tendons and gastrocnemius tendons, etc., are controlled by the motion of the knee as well. Therefore, the study of the kinematic and force interactions between the force-bearing structures during functional activities is helpful for a better understanding of the etiology of relevant diseases and for planning and evaluating subsequent treatments, such as ligament reconstruction and rehabilitation. But the problem with the determination of internal forces, remains a great challenge in biomechanics. The reason being that direct measurement of internal forces in living subjects is only possible in exceptional circumstances, such as through instrumented implants. Back in 1990s, I developed an instrument prosthesis where we input a massive femoral prosthesis into the patient with bone tumor. And we put strain gauges, and then we can measure in vivo the forces transmitted in the prosthesis. And other than that, it is very difficult to actually measure the forces inside the body. So the one way we tackle this problem is to use combined theoretical and experimental approach. That is, we calculate values of quantities that cannot be measured from values of quantities that can be measured. Let's take the loaded spring as an example. We can calculate the forces transmitted by the spring, which is not measurable, by the deformation of the spring. All we need is the Hooke's law. In human motion analysis, we need a mathematical model of the body as well as non-invasive measurements. And this is one example. In human motion analysis, another example is the inverse dynamics analysis, where we measure marker trajectories, We measure external forces from force plates, for example, and then we can calculate using a multi-body dynamic model of the body to calculate displacements, velocities, and accelerations of the body. And together with the external forces, we then calculate the resultant forces and moments at joints. Another example of similar philosophy is the invention of the CT scanner. Back in 1979, there was no scanner, a CT scanner. There was only X-ray. And Dr. Cormack was a nuclear physicist. He had to supervise the amount of dosage of the X-ray. So one day he realized that the input of the X-ray, you can measure it. You can also measure the output of the X-ray. And the only thing is the attenuation of the soft tissues in the body that can determine the output. So it occurs to him that F is the variable absorption coefficient along the line L. So if F is a function in 2 dimensions and G is known for all lines intersecting the body, G is the ratio, the log of the ratio of the input and output X-ray dosage, then the question is, can F be determined if G is known? So by solving a mathematical problem, he earned a Nobel Prize in medicine, and by an indirect way. So today in this talk, I'm trying to demonstrate the feasibility of calculating values of kinematic and mechanical quantities of a joint that cannot be measured non-invasively in vivo, from values of quantities that can be measured using image-based techniques that we have developed over the years back in Taiwan at the National Taiwan University. So the approach is basically based on the integration of the medical image-based techniques, infrared stereophotogrammetry, and finite element modeling. So I'm going to focus on the explanation of 3D radiographic measurements and its integration with infrared stereophotogrammetry and finite element modeling, and to explain the application to study various activities. And for this conference, I've chosen cycling as an example. And the soft tissue artifacts, because I'm sure a lot of people here using marker-based stereophotogrammetry systems to do your studies. And we know the soft tissue artifacts would affect the results of the calculated results. So I'm going to show you how the soft tissue artifacts would affect the calculated mechanical variables during cycling. And in the end, all these methods will involve radiation dosage. So I'm going to introduce another new method we have developed in collaboration with the Siemens in Germany. It's called a sliced volume registration method, so that we can do dynamic 3D MRI. And stereophotogrammetry, I'm sure you all know this. You know, since the year of Edward Muybridge, and this is the Google Doodle in 2012. I just take it up to celebrate 182nd birthday of Edward Muybridge, the father of photography. And since that day, we now have the ability to combine 2 cameras, similar to our 2 eyes. As long as the marker is seen by at least 2 cameras, we can reconstruct the position of the markers in space. And this is the stereophotogrammetry principle. And so since then, over the last few decades, marker-based stereophotogrammetry has been used, applied to all aspects of human motion analysis, including clinical motion analysis. And these are the data we use to study children with cerebral palsy. So marker-based stereophotogrammetry has all the advantages in providing non-invasive 3D dynamic information. But it suffers some limitations as well. For example, the skin movement artifact of the markers would affect the calculated results, and the detail of the bone kinematics cannot be measured directly. So one way of solving it is to establish an anatomical-based mathematical model of the musculoskeletal system you are interested. And this is the model I developed back in 1996. And we use this in combination with skin marker data and the ground radiation forces to calculate the forces transmitted within the femur. For example, here is the ground radiation forces, and the yellow line is the measured axial forces in the prosthesis, and the green line is the calculated using the model. So a model like this helps us to go further to understand the musculoskeletal geometry and the loads transmitted. And nowadays, we have all sorts of commercialized software packages, including the antibody modeling system, OpenSim system, live mode, etc. These tools are very helpful for studying human movement. But the problem remains that we are facing the musculoskeletal system as a redundant system. In other words, there are more joints and muscles than are necessary for performing motor tasks. On one hand, it provides the compensation mechanisms for people when they get injured. They don't have to lie there and doing nothing. But for biomechanists, it makes the system for determining the forces in the body as an indeterminate one. So there are two possibilities. One way you can use optimization methods to solve it, or the other way is that we can reduce as much as we can the number of unknowns. And I'm going to show you in this talk how image-based methods can probably contribute to that regard. So traditional medical imaging methods, there are a lot of medical imaging methods that potentially can be used to measure joint kinematics. But there are advantages and disadvantages. For example, traditional X-ray, planar radiographs, it shows the interior of a joint. You can see the details of the bone, but it's 2 dimensions, and it's static planar imaging. We can't use that to study movement. We can have, thanks to Professor Cormack, we have a CT scanner that allows us to get 3-dimensional information of the skeletal system. And we can use that to reconstruct in 3 dimensions of the bones. But normally you take CT scans in a supine position, and it only provides you static information. And a step further, we can have MRI as well, magnetic resonance imaging. The MRI has the advantages of getting information of not only skeletal hard tissues, but also soft tissues such as ligaments and muscles. So we can use that information to reconstruct the geometry of the joints. But the MRI normally has to be taken in supine position. And the scan takes a long time. You can't move in the scanner. So it's basically a static measurement modality. So if we are interested in dynamic movement, we have to look into fluoroscopy system. A fluoroscopy system is normally used for angiography measurements. So you put the wire into the blood vessels and to look into the heart, to see the heart valves, etc. And we use this information, the system, to measure joint motion. It is low radiation dosage, and it's dynamic image information. You can see inside the joint. But it's, again, planar, and we cannot use it for reconstruction of 3-dimensional bone motion. So over the years, we have tried to use these existing traditional medical imaging methods to come up with a method so that we can measure dynamic 3-dimensional motion of the bones. And of course, we are not the first one in the world. There are nowadays more and more people interested in this endeavor. And following the stereophotogrammetry idea, it'll be easier if we can have 2 X-ray sources, mimicking our 2 eyes. So if you have 2 X-ray sources, and obviously you can reconstruct the bones in 3 dimensions. So with these methods, we can use MRI method as a model, CT, and according to the literature, it has very high accuracy, less than 1 millimeter in translation, and 1 degree less for rotations. And this method has been applied to all sorts of joints in the literature. But it does have limitations in measuring 3D joint kinematics, because biplane fluoroscopy would inevitably reduces the volume of measurement to the region formed by the intersection of their projected beams. It is unable to reconstruct 3D bone poses if any of the fluoroscopy images becomes unavailable, such as due to the obstruction of, by other body parts, or the target segment moving out of view of the view. And also, because you've got two radiation sources, the radiation dosage is higher than when you use only a single fluoroscopy source. So we started to think, what can we do if we can move to reconstruct the motion using only a single fluoroscopy? The idea is that if you have two X-ray sources, if you have a point in space, then with the intersection of the two lines, you determine the position of the marker in space. That's not a problem. If you only have one camera, one X-ray source, a point on the image can mean an infinite possibilities of the object in space. But if we know the shape or geometry of the object in space, instead of only the mount point, we can see that the projection of the object on the image varies when the object moves towards and away from the image plane. I'm not sure whether you can see this. And if you translate the object away from the position, you can also see the projection of the object move away from the true projection. And it does the same thing when you rotate the object. So by taking the projection of the object, we may be able to reconstruct the three-dimensional position of the object in space. And the first such study was done at the MIT by Professor Scott Banks. And he was the first one to use so-called model fitting approach, where he established a series of projection shapes of a given total knee replacement prosthesis, and to see the soufflate of the objects in different positions. And he then were able to estimate the motion of the total knee replacement by matching the projected soufflate of TKR model and the soufflate of fluoroscopy images. And he used normalized Fourier descriptors. So following along the same model fitting philosophy, we also developed a technique based on a similar approach. So firstly, this patient has got a total knee replacement. We know these CAT models from the manufacturer. And so the patient received dynamic X-ray. And we established a software system where we can register the CAT models to the images. And we get the three-dimensional motion of the prosthesis. So let me give you the this animation shows these are the femoral component of a total knee and the tibial component of a total knee space. So if on the computer we can simulate the fluoroscopy system, we can then move, say, the femoral component in space, and the computer generate positions automatically. For each position in space, you have this projected image on the image plane of the fluoroscopy. So we change the orientation in space, position in space, until it matches the image on the background. Once we have done for the femoral component, we can do it for the tibial component as well. And once we have registered the two prostheses to the image at one instance, we can do it for all the sequences throughout the flexion extension. And then the fluoroscopy image is retired. We can see the prosthesis motion in 3 dimensions. And we really reconstruct the motion of the prosthesis. And we can zoom in to see how the prosthesis is making contact with each other. And then using that information, we can calculate mechanical variables from that. And because prostheses are metals, so their images in the plane, in the image plane, is very clear. So they have clear contours, etc. So the accuracy can be very high if you use implants. So the component pose error is less than 1.4 millimeter and 0.7. And according to different publications, the accuracy can be around millimeter and less than 1 degrees in rotations. Now the next question is, can we use the same approach to study natural knee joint for people without total knee replacements? So people started to use a similar approach. They get CT or MRI information of the bone, and then they took the surface of the bone and imagine it's an object. And then they do similar projections to, similar to the total knee replacements, without any information within the body of the bones. So then they had to they had the error about 7 or 8 millimeters in translation, which is very big. So they had to neglect the outer plane translational component of joint kinematics. Outer plane, I mean the object moving out of the image plane. So the error is biggest along this direction. The outer plane translation component is the biggest error in this single plane based approaches. So we were not happy with that, and a theoretical study on the accuracy of surface-based methods for natural knee joint motion, they realized that even under ideal condition, the best precision was about 5.6 millimeter in translations. The reason being that the attenuated bone edge was the primary source of error, because bone attenuation edges are not like the metal prosthesis. So it appeared to be an advantage to use the inner structure of the bone and to produce the attenuated edge in bone model. So we approached this problem by developing a single plane fluoroscopy technique using so-called digitally reconstructed radiograph, DRR in short. On the left is a surface model of the femur. On the right is actually a projection of the CT data of the femur. And the bone is rotating in space, and for each instance is actually a digitally reconstructed radiograph. I just played it in sequence. So you can see how the femur rotates, and you can see how the internal structures of the femur is represented on this image. And this is called a DRR. So the sequence is that the patient, to get a CT scan, we get the CT data of the bones. The patient receives fluoroscopy imaging when he or she does the movement under investigation. Our software system registers the bones according to the images, and then we get the three-dimensional motion of the joint of the bones to a very high accuracy. And this approach is called a weighted edge matching score. So on the top is the fluoroscopy image. On the bottom is a DRR of the bone. We then do edge detection, and we dilate the edge of the fluoroscopy image, and then we compare these two according to an optimization criteria called weighted edge matching score. So the registration is based on weighted edge of the DRR, dilated edge of the fluoroscopy image. And we use genetic algorithm to find the optimum position of the bone. Again, I'd like to show you the animation of this. Is a volume of a CT, which is static and rigid. In the back is the fluoroscopy image that we've taken when the subject is doing sit to stand, sitting up and sitting down. So in the first instance, we try to match the femur. As you can see here, the femur is rotating in space. For each position, you have a DRR projected onto the image. And within the software system, try to match the projection with the background fluoroscopy image. Once the femur is matched, we can do it for the tibia. So there is a very subtle searching process. And we can then do it for all sequences of the movement. Once they've done, the background is removed. And virtually, you get a three-dimensional dynamic CT motion of the bone. We can render the bone. We can zoom into the joint. And we can see how the contact between the bones when the subject performs functional activity. we had to validate, we had to assess the accuracy. So we use cadavers, also so cadavers for the knee, for the spine, for the ankle. We have done all sorts of validation using cadavers. And with the single plane fluoroscopy approach, we got in-plane translation accuracy for less than 1 millimeter, out of plane 3 millimeter for single plane. But for rotations, the accuracy is less than 1 point. These are the biases, and these are the precision of the methods. If we use biplane approach, the translations are all less than 0.3 millimeters in either in-plane or out-of-plane translations. And the rotations are less than 0.4 degrees, which is very, very accurate. So all these WEMS, the name of the methods, all these WEMS methods developed over the years at my lab in National Taiwan University has been integrated and implemented into a software package like this. The software package is capable of single and biplane registration for both bone and metallic implants. And once any of the fluoroscopy images from biplane fluoroscopy becomes unavailable, the software system switches to single plane registration. So in other words, we won't miss any of the data, even sometimes the joint moves out of the field of view of one of the fluoroscopy source. And as a demonstration, I just show you we use that to compare, to study different types of prosthesis, knee prosthesis, fixed bearing total knee and mobile bearing total knee. Just a quick review. People in the past, they compare their total knee replacement movements to normal joints. But in fact, once you have done total knee replacements, the anterior cruciate ligament is sacrificed. So the correct way is actually to compare total knee replacement movement with a knee joint without ACL. That makes more sense, right? So we have studied normal knee kinematics during isolated knee flexion extension and during single stand, and compare with those without anterior cruciate ligament, and you can see the differences. And because of time limit, I'm not going into details of these, and just give you an idea that we could compare the kinematics between different groups of joints, and with this information can then feed back to the manufacturers of total knee replacements. Now, with these methods, we were able to measure more accurately the kinematics of the joints. And then we are interested in not only kinematics, but also kinetics and forces. So we have to integrate the 3D fluoroscopy with existing marker-based stereophotogrammetry and force plates. And if we combine these 4 together, well, the EMG is missing. I don't know why. Somebody has taken my EMG system. Anyway, we could put the 4 together, and we can measure not only the whole body motion, but also the detailed motion of the knee, and we can also measure the ground rotation forces. With this integrated system, you won't miss the wood for the trees. Okay, you can see how this and because marker-based system has been used a lot in the world, so we started to look at how the markers move with respect to the underlying bones, the so-called soft tissue artifacts. And we realized that the soft tissue artifacts of my marker appear to be varying among subjects and are affected by activities. Thigh markers, as you can imagine, that had greater skin wave artifacts than shank markers, and the STA were nonlinear in relation to the knee flexion. This is opposed to previous understanding that, or assumption that they are linearly related to knee flexion angles. And considerable soft tissue artifacts also led to significantly underestimated flexion, internal rotation angles, and extensor moments, but overestimated joint center translations and adduction during stair ascent and other activities as well. If you're interested, you can see our publications in the Journal of Biomechanics and Gait Posture. So we have combined kinematics, we combine kinetics, and then we are looking into the forces transmitted in the ligaments. If you remember, when I started, the purpose was to solve the indeterminate problem. I try to provide more information for the low-bearing, force-bearing structures, try to reduce the unknowns. So we combine finite-element modeling as well. Okay, so But the model is subject-specific because the geometry of the joint can be obtained from the CT. The motions of the bones are from the 3D kinematics fluoroscopy system. And we do the so-called arthrometer, the KT2000, to collect the stiffness of the joint information so that we can fine-tune the mechanical properties of the ligaments so that the mechanical properties are, as much as we can, subject-specific. And this was done by a KT. So we have the finite model, and we change given the boundary condition, we change the mechanical properties, and then we match the stiffness curves so that the whole finite model is customized to the specific subject. So it takes a lot of time to analyze one subject for a certain activity, and this is the process we use to fine-tune the mechanical properties. But how do we know the whole process is correct? We have developed a robotic joint testing system. I'm not sure whether you know this, but Professor Wu started with this approach. We use an industrial robot, and through feedback control, we can control the motion of the joint while minimizing unnecessary forces in different directions, different degrees of freedom. So we did the experiment for 0, 30 degrees, 60 degrees, 90 degrees, and 120 degrees during draw test. We measure force and displacements. And we use only the 30 degrees to simulate the Lachman test to fine-tune the mechanical properties. And once we have that, we can then use the Finite-Element to analyze these other angles as a validation. So we use 30 degrees to fine-tune the parameters, and we check whether these are okay when compared to data from other angles. And so basically, we try our best to validate the finite-element analysis procedure. So for this particular conference, we started doing some cycling study, okay, because I believe it is more interesting to the audience here, I hope. So I'm going to talk about the application to cycling. For rehabilitation purposes, patients with ACL reconstruction, we use cycling exercises as a safe rehabilitation modality for those with ACL reconstruction. Because Bayanan, back in 1992, they used a Hall effect sensor to measure ligament strain in vivo during cycling. And they show that the loads transmitted in the ACL during cycling is minimum. So it is safe to do ACL reconstruction rehab. So after that, cycling exercise have also been used to rehab the knee joint even after PCL reconstruction. There are a lot of PCL reconstructions in Taiwan, and all the physiotherapists, they use cycles as a rehabilitation procedure for those with PCL reconstruction, even though it is not clear whether cycling is safe for the PCL at all, because the PCL limits tibia posterior translation, whereas the ACL limits tibia anterior translation. So even though the two cruciate ligaments have very different mechanical function, people use cycling as the single rehab modality for the reconstruction, ACL and PCL. So because they are different, so I was wondering whether backward pedaling would be safer for PCL reconstruction. So what I'm going to show you is the study using the method and to compare the forces and loads transmitted by the ACL and the PCL during forward and backward pedaling. So we've got 18 healthy subjects, and each of them wear 28 markers on the body so that we can track the motion of the pelvis, thigh, shank, and foot, and their left lower limb, etc. So as you can see, the whole setup is, to be honest, quite complicated. It took every time 10 people working together to put everything together. We've got 20 Vicom cameras all connected, and we got, well, I'm going to talk about that later on. And so the task is to do cycling at an average power of 60 watts, and the peak watts is 137. It's very typical for ligament rehabilitation. So the experimental setup is that we have a biplane fluoroscopy with a ganometer, a cycle ganometer, very purposely built for this purpose. So the patient receives CT scan of the joint, and we have two cameras, two Vicon systems connected, one as master and the other one as slave, so that we can have 20 cameras. It's all surrounding the patient. And the pedal is instrumented with a 6-axis load cell so that we can measure the pedal reaction forces. And we put 4 markers there so that we know the direction of the ground reaction forces. And similar to our medical imaging methods, so we measure here, we got biplane fluoroscopy images here, we got the CT scan of the model, and our software system would register the two together and to get the motion of the knee. And not only the joint, but also all the markers on the body, and also the pedal reaction forces. So these are the results. As you can see, this one is forward pedaling, and this one is backward pedaling. And the pink point here is the hip joint center, and the blue point here is the ankle joint center. The 4 little pink markers identify the pedal load cell. Well, it's remarkable to me that the pedal reaction forces look quite similar in both forward and backward pedaling, except that there is a slight difference at the ankle, mostly. And in front plane, the pedal reaction force is directed medial to the knee joint and towards approximately the center of the midpoint of the 2 joint centers of the hip. So in graph form, the previous one is animation. In graph form, you can see the moments and forces. So the joint forces and moments, they have comparable peak amplitudes, but at different crank angles during forward and backward pedaling. Well, this is a quite busy animation, but we do spend a lot of time trying to put together all the information, both kinematic and kinetic data. The upper row is forward pedaling, backward pedaling. This arc with color is the muscle moment. And this red vector is the pedal reaction force. We just transfer the point of application of the pedal reaction force to the center of the knee joint, so that you can see, and this little clock here represents the pedal, and you have the pedal angles here. So forward running and backward. So you can see around the top point, the muscles exerting a lot of effort to extend the knee. And the color map here, you see from the top, this is the contact area. So the bigger the area, the greater the force transmitted by that compartment. So as you can see, the the pedal reaction force is directed medial to the knee joint. So the medial compartment of the knee transmits much greater load compared to the lateral compartment. So it's quite intuitive to see how the kinematics and the kinetics and loads are interacting with each other. But of course, it took me, I can see this animation for 1 hour without stop, trying to understand how it all works together. And if you observe carefully enough, this is the end of the femur. If you see, it moves. Come on. It moves down in this direction, and then a different path backwards. Can you see that? So the knee is coupled. During powering phase and recovering phase, the rotation of the knee joint is different. So they follow different paths during powering and recovery. And this is also different between forward and backward. So the differences between forward and backward are really subtle, but you have to observe carefully. And perhaps we can see in graph forms. Well, I don't expect you to resolve all this. But the summary is that the knee joint center is more anterior during backward pedaling when you compare to forward. And the knee is more extended and internally rotated during backward pedaling. And the joint space, which indicates the contact force, is smaller in backward pedaling than forward. So in other words, when you do backward pedaling, it is possible that the contact force, in other words, the force transmitted by the articular surfaces, may be much higher than when you do forward pedaling. So this would have a very good indication for people with knee osteoarthritis if they use cycling as a modality to rehab in these patient groups. And when we compare the two compartments, the lateral compartment showed more anterior, and the contact points in the lateral compartment is more anterior during backward pedaling, and more posterior during backward pedaling in the second half, around the crank angle from 135 to 315 degrees. And the middle compartment, the contact moves more anteriorly during backward when compared to forward. So these are the graphs, just to give you an idea. I've got 3 minutes to go. So these are the finite element results. Well, I just use this to confuse you. All black. But if you observe carefully, the posterior cruciate ligaments has more red color, indicating that the stresses and strains experienced by the PCL is greater than the anterior cruciate ligament. And these are the resultant forces for each of the ligaments. As you can see here, the PCL transmits around 450 newtons, either during forward or backward cycling. And whereas the ACL transmits around 20 newtons. That's interesting. When you, during the power phase, you exert a lot of quadriceps force. But because the knee flexion angle is high, the patella tendon is directed posteriorly. So it's actually pulling the tibia backwards and then load the PCL instead of the ACL. When the knee is extended, there are not much quadriceps force. So the ACL is not loaded very much. So basically, this is the results, which is consistent to what we have known in the past. And soft tissue artifacts, I suppose people here are more interested in this as well, because we use markers. We put markers on the body, and we do cycling studies, and we use markers to calculate joint moments and forces, etc. And if we are standing on the femur, you are looking at the markers on the thigh. The gold standard, in other words, the bones are in pink. So you just look at the yellow dots. The yellow dots are the skin markers. The yellows moves relative to the pink ones. Those are the skin markers for the thigh, and these are the skin marker areas for the shank. And in brief, skin markers significantly underestimated the knee flexion and adduction angles for knee flexion of more than 30 degrees. Skin markers also overestimated the posterior and distal joint center translations, but underestimate the lateral translations. Skin markers significantly underestimated the extensor moments for crank angles over 326 degrees and less than 131 degrees. Or if you're interested in this number, I can give you after the talk. I've got 33 seconds. The abductor moments were significantly underestimated for crank angles. So in summary, forward and backward pedaling showed different rigid body and surface kinematics and kinetics patterns, as well as ligament loadings. The PCL transmits greater loads than the ACL during both forward and backward pedaling, indicating a greater risk of injury to the reconstructed PCL during rehabilitation with cycling. So caution should be exercised when you use rehabilitation using cycling. And obviously, other parameters can affect the results as well. You can change the height of the seat, you can change the resistance, etc. We are not consider those parameters in this study, but this is a beginning of basic knowledge. Significant errors were found in the calculated kinematic and kinetic variables during cycling, and mainly due to the skin movement artifacts. And further development of the compensation methods may be necessary to improve the calculated results. Well, so if we know the forces in the ligaments, and we can then reduce the number of unknowns in the indeterminate problem. So to me, it is a step further to try to solve the long standing problem of indeterminate force distribution. And before I leave, Madam Chairperson is there waiting for me. I'd like to leave with the slice to volume registration. So the Siemens has developed a fast single slice or two slice dynamic MRI. So we were collaborating with each other, and I collect single slice MRI and try to reconstruct three-dimensional real-time 3D motion. So firstly, we scan the knee in 3 dimensions during static condition. And then we take 1 or 2 slices of real-time slice. And for each instance of the slice, we use the MRI static slice, static scanned bone model and try to match with the single slice. And then we can do it for all the slices. And once we have done, we got a real-time 3D MRI imaging. So we can get rid of the single slice information to get 3D motion. And we are developing new devices where we can put into the MRI scanner so that we can apply loads and stresses to the knee. And we can study how the soft tissues transmit loads. And we have done validation experiments. Because of time, I'm not going into details of that. And we have shown that the translations are less than 0.5 millimeters for the femur and for the tibia. And the precision, these are biases, and the precisions are less than 0.4 for most of the components. So in conclusion, fluoroscopy-based techniques seem promising in the 3D measurement of joint kinematics during functional activities, especially for those of you who are interested in sports with high speed, high resolution, but low radiation systems emerging. So this method, I believe, will have more clinical and sports applications in the future. And the 3D measurement of joint kinematics via dynamic MRI deserves further development. And I hope I would have another chance to share with you our new developments on the dynamic MRI in the future. And I'd like to thank my collaborators in various universities in Taiwan and the financial support from our government, Ministry of Science and Technology of Taiwan. And lastly, I would like to, for my own self, I'm organizing the 14th International Symposium on 3D Analysis of Human Movement in 2016, July 18th, 21st. And this is our webpage, and you're most welcome to visit our webpage, and I hope that I can see you again in Taiwan next year. Thank you very much for your attention.